Today, we're going to talk about the time other physicists broke physics. Um, so, modern physics, which is generally considered any physics from 1900 onward, uh, not only is some of the most influential physics we use today, but also modern physics as a class was like my all-time favorite class in undergrad. So yeah, today I want to talk about two of the important experiments slash developments um, that motivated the development of these modern physics ideas. Um, and one of the things that I loved about my modern physics class um, was the textbook we used, as well as the way the professor taught it, was taught with the historical context in mind. So, like, uh, what was the physics they had to work with back then? What were the issues they found at the time, and why they felt it important to reconcile those issues? So, yeah, without further ado, I will get started. So, hang on, give me a second. Load chat. Okay. All right. So I don't know why you moved over here again. I don't like it when you do that. Just stay over there. All right. So, no, I don't like it when you're here either. You stay over there. All right. So, prior prior to 1900. Prior to 1900, people had various scientists and people much smarter than I had developed basically all of classical physics, the way we typically describe classical physics nowadays. So, we had the notion of classical mechanics, which is the study of how and why objects move subject to some force or energy. So, this would be, Newton, uh, Lagrange, and my personal favorite, Hamilton, among many others. But those are the three, giants. Um, and we also had classical uh, electromagnetism, which I'm just going to call E and M. So this is Gauss, Ampere, and most importantly for this topic, Maxwell. And then finally, we had classical thermodynamics, which I'm just going to call thermo, and statistical mechanics. So this would be Boltzmann, if I can draw it, write it. Boltzmann, I believe Gibbs was also in the 1800s. Oh yeah, Ampere was GOAT. Um, but yeah, so primarily Boltzmann. And so the first discrepancy we're going to talk about involves these two areas. Um, I'd also like to, before I get into this, the state of physics at the turn of the 20th century. Physicists at the time thought this was it. You had classical mechanics, you had E&M, and you had thermodynamics and statistical mechanics. That was it. As Lord Kelvin once said, all that is left for physics to do, or for physicists to do, is better and more refined measurements. But the theory is finished. Except for three tiny, and I do use tiny in a litotic way, three tiny discrepancies, two of which I'll talk about today, and I want to save the other one, the third one, for another time. So, first one, that involves classical mechanics and E&M. So, in classical mechanics, you have this notion of relative velocity. And specifically, we call this Galilean relativity. So, what this means is that let's say I'm on, you know, a dock, right? And you have a river in front of me, and then we have a boat with Tyler on it. And let's say that this boat is moving with velocity, or sorry, let's say that the river is flowing to the right at v equals 10 meter per second. And let's say that Tyler on the boat is moving at script v, let's say 20 meters per second. So what's important here is relative to what, right? So if the river itself is moving, the boat is going to naturally want to move with it. So if your speedometer on the boat says 20 meters per second, I know boats don't use those units, that is your velocity with respect to the river. There's an R. Like, you are moving 20 meters per second relative to the motion of the whole river. But the river is moving relative to me. So if I want to calculate Tyler's velocity relative to me, um, yes. Um, yes, it is 10. Good job. Yeah. So the velocity relative to me, which I'm going to denote v prime, is equal to, yeah, the velocity of you relative to the boat minus the velocity of the river. And the reason why it's minus, what I like to use is sort of like a transitive property, right? So this is the velocity of Tyler with respect to the river, and the v is the velocity of the river with respect to Gauss, let's say. But, oh, wait, yes. Yeah. So then I want to do minus the river with respect to Gauss. I want the same object, whether it's with respect to or the velocity of, to be in the middle. Because this is going to be the velocity of Tyler with respect to Gauss. So yeah, like you said, it is in fact 10 meters per second. No, it's, sorry, you tripped me up. It's 30 meters per second. Sorry, it's 30 meters per second. Because, like I said, this is the velocity relative to the river. You're moving 20 meters per second along with the river. Yeah, the river itself is moving with an additional 10 meters per second. All right. So yeah. So yeah. I tend to use this kind of mental trick to make sure I have my um addition right. So you want whatever reference frame or whatever object is canceling out, you want it to be in the middle. So yeah. So that's Galilean relativity. And the key point of Galilean relativity, which I will write here, the key point of Galilean relativity is that speed is relative. There is no absolute notion of speed, right? Because I can just move to another reference frame and that velocity is going to change. But that contradicts something that was discovered as a result of classical electromagnetism. So, in classical E&M, Maxwell developed four equations, or he didn't develop them. He collected them and wrote, transformed them into a more concise form, and then grouped them all together. That's why they're called Maxwell's equations. And so a consequence of Maxwell's equations, um, that I will get to later in my E&M series, is that you can you can combine Maxwell's equations in a clever way to get this equation. Uh, no. Mu naught epsilon naught partial squared E partial T squared, and the same for the magnetic field. So, anyone that has been paying attention to Z's PDE series, can anyone tell me what PDE this is? Anyone? Oh, that's fine. This is. I gotta get back to the tab. This is the wave equation. So what Maxwell found out was that electric and magnetic fields can form waves. And the general form of the wave equation is the Laplacian of u equals 1 over v squared d squared u dt squared, where v is the wave speed of your wave. So that tells us that this mu naught epsilon naught, which is the magnetic permeability and electric permittivity of free space, respectively, these represent 1 over the wave speed squared. So mu naught epsilon naught equals 1 over v squared. And I'm going to call it v for right now, but this ends up being the speed of light. So this tells us that v equals 1 over square root mu naught epsilon naught. So this velocity, despite the fact that I just said that Galilean relativity says that velocity is relative, tells us that this velocity is constant because mu naught and epsilon naught are universal constants. They will not change depending on your reference frame. So that means in every reference frame, the speed of an electromagnetic wave is 1 over root mu naught epsilon naught. So therein lies the discrepancy, right? Is Galilean relativity wrong and velocity is absolute? Which means there is a preferred reference frame the universe writes all of its laws in. Or is Maxwell wrong and this wave equation is wrong? Well, intuitively speaking, we want to say that Maxwell is wrong, right? Because we experience Galilean relativity every day, right? If you're on like a train, you'll notice everyone around you looks like they're standing still. Meanwhile, like the outside is rushing behind you. But someone on the outside would notice you moving forward with the train, as well as everyone else on it. That is an example of Galilean relativity. So physicists at the turn of the 1900s assumed that Maxwell was wrong. And hang on. Sorry. And there is a preferred reference frame for light. Just like any other type of wave. What that means is whenever you're dealing with the wave equation for a mechanical wave, right? So like sound. Sound waves require a medium. Usually air or water or metal. Sound waves need a medium, a material to propagate through. Same with like mechanical waves in a guitar string or ocean waves. So what that means is that when you have the wave equation for sound, this velocity is relative to the velocity of the medium itself, which sets up the medium as a preferred reference frame for these waves, right? It makes things easier to calculate if we just work within the reference frame of the rest frame of the medium. Does that track so far? All right. So that led physicists to assume that light had a medium. And they called this medium the hang on, I gotta look how to spell this. Luminiferous ether. And that the speed of light, c, which equals again 1 over mu naught epsilon naught, was with respect to this ether. And so that means that you should be able to, if you had, say, like the solar system, right? Let's say that's the sun. Earth is out here. Da, 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 da. There is some direction that this ether is traveling in because it's a medium, right? And that means that to any other reference frame, the ether itself should be moving. But this is only the ether must only have one direction, right? So that means that logically, if the ether is moving this way, for instance, then the speed of light, I'm going to use C perpendicular. The speed of light in this direction should not be the same as the speed of light in this direction. Right? Because C is with respect to this ether, which means that in this direction it should be going faster than C because it's moving with the medium. And this should be just normal old C because it's moving perpendicular to the motion of the ether. So using this intuition, this prediction, this assumption, it was a couple of people, but the people famous for it, the two people famous for this, Michelson and Morley, they developed an experiment. So, Morley. They created what is called an interferometer, which this type of interferometer is actually still useful today. And in fact, one of the most famous usages of a Michelson-Morley interferometer is LIGO. That's how they detected gravitational waves. A giant interferometer. But I will leave that for tomorrow's stream with Aleph and Z. But yeah, if you want to know more about that, check them out. So the principle behind it. Let me see. Yeah, okay. So the principle behind it, right? You shine a beam of light, and it passes through a beam splitter, right? So a beam splitter just splits the intensity of light 50-50. So half of your light transmits through your beam splitter, half of it reflects at 90 degrees relative to the beam splitter. And so you put a mirror here and a mirror here at equal lengths, which we will call L. So L is this length and L is this length. I apologize, it is not drawn to scale. So, if these are mirrors, mirror 1 and mirror 2, what will happen is this light source will get split by the beam splitter. One half will travel here and bounce back. One half will travel here and bounce back. And this returning light will pass through the beam splitter, or at least half of it. And then half of this returning light, so half of this returning light, will get reflected and enter our detector. And so you have to remember, light is a wave, right? And waves are the simplest of waves, a sine wave. Sorry. Given that light is a wave, waves exhibit a behavior that we call interference, right? So if you have two waves that are out of phase with each other, basically they're offset by 90 degrees, they will cancel each other out. That is destructive interference, and you'll be left with nothing. Meanwhile, two waves that are completely in phase will constructively interfere and add up. And so what causes this phase difference? Hey, Comey. Yeah, cancel culture is real. So what that means is this phase difference is caused by a difference in path length, right? If these two light waves travel the same distance, then they'll have the same phase when they hit the detector, and you'll have maximum interference. But if one of the arms has to travel further or moves faster because of the ether, then that changes its phase slightly, right? If it's moving faster, it'll appear at the detector slightly before this arm, which means that the phase will be slightly earlier than this arm, and you'll have some sort of interference in between constructive and total destructive. And so that was the principle of their experiment. They were expecting there to be interference, right? Because they thought there was an ether. Oh, what did that do? All right. They thought there was an ether, which means they. Here, I'll write this out explicitly. What Michelson and Morley expected. They expected to see an interference pattern caused by the mismatch of the speeds of light. And so I can go through all the math that it shows explicitly what the phase difference they were expecting to see is. But I want to keep this as conceptual as possible. And the specific math isn't important because what they saw no interference. This is one of the most important null results in the history of physics. They saw no interference. The speed of light was completely identical, perpendicular, and parallel, which tells us there is no ether. So no interference implies no ether. So where does that leave us, though, right? Because I said classical mechanics said one thing, E&M said another thing. We just showed that E&M is right, that the speed of light is absolute. So we're left to assume that... Oh, hang on. We're left to assume that Galilean relativity is wrong. So the correct answer is classical mechanics is wrong. More specifically, classical mechanics is a low velocity limit of what we now know as special relativity. And yeah, so I'm not going to go into relativity. But yeah, this is what led. Well, this is one of the important discoveries that motivated relativity. They proved that the speed of light was absolute, which showed that classical mechanics was wrong, which meant that they needed a replacement for classical mechanics at high speeds that reconciled with the idea that light has an absolute speed. That is why they cared about relativity at the time.